This neat little thing is an ionizer lamp from China, and the most interesting thing about it is that it contains this very, very tiny high voltage power supply. And I've already stripped one of these apart. It had to be depotted from the resin. Quite complex, took a while, but the interesting thing is it uses a component you may not have come across before called a SIDAC. So let's investigate this, shall we? So the idea is that this doubles up as not just a lamp hanging from your ceiling, but when it's on, these little carbon fibre bristles at the end are charged at a high negative voltage, and it creates a stream of an electrical charge into the air. And if I should show you it lit, shouldn't I? That's a good thing. Before I start taking it to bits, I do have another one I'll show you at a moment anyway, but let's test this one anyway. I've just scattered components in from the left-hand side because they were for a later part of the video, but they've made a premature appearance. So you turn it on, it lights up, and you won't really detect much. I can feel it, actually. I can feel the stream of ions going onto my hand. It's a fair low-power lamp, not that exciting, but let's open it up. That's what's interesting. Incidentally, its power consumption, it's got terrible power factor, as you'd expect. It's capacitive dropper, and it is dissipating about 2 watts of power. So I'm going to pull this carbon fibre in bunch out here. And this circuit board I'm going to lever out. Where is my screwdriver? I've misplaced my screwdriver momentarily. Let's get this out. Let's short capacitors that may contain little surprises. I think that's most of them. I'll just put my fingers over it. Yes, it's discharged. And let's find the interesting component. The interest component is stuffed down into the base down here. This is it. Let's zoom in just a little tiny bit for this. So we've got the main supply coming into the lamp, and it's going onto this ordinary sort of capacitive dropper based circuit board. I won't even take a look at that, it doesn't really matter. But tapped off the other side is the ionizer module, which has the high voltage wire with a tuft of carbon fibre bristles, and it's got basically a red and black cable just going up and just tapping onto, well, does it actually, have they really? No, they've got the black one onto the live effectively and the red one onto the neutral. It doesn't really matter. The polarity isn't really important here. Let's lop that off, because the bit that's really interesting here, and the lamp will still work now, it will just be a very ordinary non-ionizing lamp. I shall just sit that back in. I shall clip the lid back on. Oh, boring 2-watt lamp. But this is the bit that's interesting. This is the bit we want to see. And unfortunately, as with so many of these, it is potted in this really brittle, hard resin. And that makes exploring it quite difficult. But there is a technique you can use. If you put this in a jar with a lid, with acetone in it, and just leave it. Now, I found that the acetone did not dissolve the red plastic here. It's a sort of hard, brittle, thermoplasticky stuff. You have to break that off, and that's quite hard. I got most of it off. I started soaking it in acetone, and literally it takes days at a time because it penetrates in so far and then it stops. And it makes the resin sort of fluff up and go crumbly, and then you can pick it out. It also destroys all the components in the process, which doesn't really help that much. Now, once I picked it all to bits, this is what I found inside. Oh, that's good zoom position. Let's snap down onto the image down here. The two 22k resistors are new because the ones that were in it were in a bit of a mess by the time I'd finally got them out. So we've got a little capacitor rated about 100 nanofarad, and I'm going to guess that they've probably skimped and they've rated that 100 volt because they've not really been taking component ratings too seriously in here. We've got a diode, which I'm going to guess is at 1N4007. We've got I've drawn a Z as a 7. That's because I was thinking, what's the next component? I thought, it's the SIDAC. And the symbol for a SIDAC is a Z with a stripe through it. That's why I actually put a Z. That's a little insight what's going on in my mind when I make these videos. Here is the SIDAC. Go on eBay and type in SIDAC, and you're not going to find many. The ones you do find are going to cost about £10 each. It's one of those components. It's cheap if you're a manufacturer with lots of applications for it, but if you try and buy one yourself, it's going to be expensive. But they're a specialist component. If you're a heating engineer or a facilities management operative who works in heating systems with gas igniters, you've probably come across this component. You've seen it without actually realizing you're looking at a SIDAC. Then here's the magic. It's a little transformer. and it's got a core inside it with a fairly coarse winding inside, and then it's got these three separate bunches of windings. I'm going to guess there's roughly about 2,000 volts across each one of those, adding up to in the region of about 6,000 volts. It's a tiny transformer. Let me show you it for real. It's tiny. It's minute. It's small. The whole circuit board is small, but you'd expect that of the way it's potted in. It was kind of potted in this direction in the container. On the output of that transformer, we've got a big high voltage diode, and then a ceramic capacitor. The coating is just etched off. That had a blue coating on it, but it gives you an indication of the construction. You've seen the Class Y capacitors for electrical safety. They're basically a metallized layer on either side of a piece of ceramic, and the ceramic, it's the thickness of the ceramic that is the insulating factor. And it doesn't look like, that little circle there would really have much capacitance, because, there it is there. It's tiny. I'm going to have to point it with my pinky. It's tiny. So that's about 4 millimeters diameter, those little metal discs. How would that equate to? That's just over 1/8 of an inch. And that's enough. With one of those on either side, that's enough for the capacitance, which is in this case about 100 pico. 100 picofarad. Is it 100 picofarad? Yes, it is. Then on the output of that is this just awful 20 megohm 8th watt resistor. This thing here, this little resistor here, is not quite everything between you and the mains, but it's most of what's between you and the mains, and it's not great. But anyway, let's take a look at the actual circuit of this. Oh, you know what? Oh, no, I'll test that afterwards. I'll show you actually working afterwards, and we'll do some other tests compared to another ionizer. Here is the circuitry. So what we've got is two 22K resistors. They've used two to kind of spread the dissipation down. It may also be a last resort safety factor to limit the current if someone does come in contact the output. And this tiny little 8th watt, which is rated for about 125 volts or something like that. That's the wattage rating, isn't it? 125 milliwatts. But it's rated real low voltage. It's not rated for this at all. I would say that if you get one of these and you want to use it, because you get big ones that have multiple outputs, I would say there's no harm in chopping this output wire and sticking a couple 1 megohm resistors in series and putting a bit of heat shrink over them. That would be an extra layer of safety against the unknown electronics inside these. So here's how the circuitry works. There's a capacitor in series with the primary of that little transformer, this dinky little transformer here. And that 100 nanofarad capacitor, this red one that looks really scrappy because all the coating came off it, that charges up via this diode here, and these resistors limit the current. So it's quite odd to look at it because it's effectively the diodes pointing in the opposite direction of what you'd normally. It sometimes makes things a bit harder to understand, but it is effectively charging that end up positive and this end is being sort of negative, because of the way it's going. Okay, when it reaches a voltage of about 100 volts, this device called a SIDAC suddenly just shunts, and it dumps. It's almost like a trigger-controlled thyristor is the best way to describe it. It latches on. As soon as it reaches its threshold voltage, it self-triggers, and it suddenly shunts the capacitor and the coil. And initially when the capacitor was charging up, the current was low, so nothing really major got induced in the coil. But now, because it's suddenly shunted it, a sudden current pulse fires through this coil. And that induces a current pulse in the secondary winding, the high voltage one, which then gets rectified by this diode, because bear in mind it's also going away from the output because it is a negative ion generator. And it dumps the charge into this capacitor, and that's where the ceramic capacitor has quite a lot of advantages. It's got a very low impedance, so it can catch that charge. So that capacitor is suddenly charged up to quite high voltage. And when the voltage is high enough, which is almost instant, then current starts flowing through this resistor and creating the negative charge in the air on the basis that because those carbon fiber strands are so ultra thin, seriously, if you zoomed up the microscope, you'd see they were just a clump of super fine strands. And if you compare it to a needle, the needle would actually look a bit like that. The carbon fiber strands are a great easy upgrade. I'll show you that as well afterwards, to an ionizer to make it more efficient in its output. But The area of charge is greatest on the sharpest point. These have loads of sharp points at the edge, and because they're charged negatively, and it basically puts a charge onto the air in the vicinity and then repels it away. So you get the charged air molecules with an extra charge going away from it. And that just repeats, because once this is discharged that capacitor repeatedly, it discharge it repeatedly. Once it's discharged it goes below the threshold that this can actually stay latched on. It probably only does it once every full mains cycle. In our case, 50 times a second. In the case of America, 60 times a second, or other places that have 60 hertz. But then it cuts off just like a thyristor and refreshes again, resets and waits for that 100 volts. And I'm going to demonstrate that. I've got a little setup here to show you that. But the return path, and I'm guessing this is why they put that diode there. They could have actually put the diode there. It wouldn't really have made much difference. Maybe they just did this because it was easier to lay the circuit board out that way. But they could theoretically have just stuck a diode there. And then had this going straight through. I don't know why they did that. It's just maybe as I say, the layout of the components was easier, and it is an incredibly easy layout. The resistors are just going on like that, and then the diodes just joined together and in a bridge. So it was a very, very simple circuit. They're probably just thinking of the spacing. But the return path from negative current flow is that it's going through the coil and then through that diode to the mains, and that is providing it via the mains. It's going to get its reference to ground, and that's what the charge is going to then charge dust, and it's going to separate out to the walls. Very interesting little circuit. In the heating systems, the SIDAC is used in the same sort of arrangement, but it's simply, in that case, it's simply a couple of electrodes and it's the ignition pulse that strikes. So it's the same arrangement. It's a resistor, capacitor and diode and the SIDAC, and it just keeps pulsing the much bigger transformer. It keeps going with that spark to actually ignite the gas. Very, very interesting little circuit. Let's explore things. I shall put that out the way and I shall show you what I've set up here. Actually, I'll doodle what I've set up here. It's a scary bit of circuitry. Here is what I've done. I've got live, to demonstrate the SIDAC, I've got live going via two resistors. And in this case, I've used 100k for speed, 100k resistors. And they're going and charging a fat, juicy, and very painful to touch electrolytic capacitor. And, oh, I've just actually drawn that the wrong way. Not to worry, let's just pretend I didn't draw it that way. I could have actually just reversed the drawing, not to worry. The diode is charging that up, so this ends up positive and that ends up negative, and those limit the current. Then across that, I've got the LED and the SIDAC, which is drawn as the Z with a line through it. And then I've got a resistor, and the resistor is, in this case, 1k, but I just used a big chunky resistor. Let's test this. This is how I initially tested to see what the voltage was. I actually put a 1 megohm resistor in, so it slowly charged the capacitor up, and I could actually measure the voltage across capacitor until it triggered. SIDACs are usually bidirectional devices, but some of them are polarized. I've come across polarized ones. I think most of them are bidirectional though. I don't know what the markings on this one, I don't know what this is because the markings have all gone. Let me bring up the quick test and plug that in and show you this working. So I shall stuff the wires into the Cliff quick test, which is used for workshops and maintenance places to test electrical equipment, easy connection. And I'm going to just bend this down, point the LED up. We'll zoom down just a little bit so you can see this better. I'm going to close it down, and after a while you'll see the LED flash. And what's happening there is this capacitor is charging up to about 100 volts, and it's a very brief flash. I don't know if it'll be caught every single time. The rolling shutter effect might miss it. It's not always being caught in camera because it's a very brief flash as it triggers and it discharges quickly from the capacitor. It's interesting that the camera doesn't pick it up every time, but rest assured it is flashing on a regular basis. I shall now discharge this capacitor so I don't get a zing off it. Is it discharged? Yes, it is. So that's the SIDAC. Now what can I do? Oh, I know what to do. Let's test the output compared to an existing ionizer. So I'm going to zoom out for this. Let's bring in some test equipment. Isn't it really amazing that this little module here can generate such a high voltage? The slight downside compared to an ordinary ionizer is that a traditional ionizer that has circuitry like, brings in traditional ionizer, which is probably charged. Circuitry like this, a lot more complex looking, but in terms of reliability, I would say I'd still choose this over this. The upside is this does fit in a small space. They probably do versions that are better suited for 110 volts because that's not really practical with a multiplier like this. But I would choose this one over this for reliability because I think this one would just last longer. This one has very high voltages in a very small area inside it. And it has that capacitor being pulsed with high current pulses, well, relatively high current pulses. One thing I didn't mention was the impedance of the windings. Because that's a high voltage transformer, the secondary is actually about 1,200 ohms because it is very, very fine wire and lots of it, whereas the primary winding was less than 1 ohm. I just thought I'd mention that. So that will limit the current, the discharge current. Oh no, it won't, because that capacitor is seeing those spikes because it's in the primary, which has a low resistance. So that stresses that. It stresses that horrible little resistor. And it's just that transformer is fitting several thousand volts in that tiny area. It's just, you know, ultimately it's a sort of weakness. Right, let's get this out of the way and bring in the test equipment. The test equipment is a cheap, shitty meter. I call it a shitty meter. They're not that shitty. They're actually very acceptable because they work. They work absolutely fine for many applications. And I'm going to put the negative terminal onto a ground reference. The soldering iron is off. Unfortunately, while testing this, I actually turned the soldering iron and forgot about it and melted the clip. Not to worry. So that is my ground reference. I'm going to turn this round to, say, 2000 millivolts, and it's showing a very slight negative charge already in the air, even as I put my hand up to this, or maybe if I rub it with plastic. I'm not really sure if that would have an effect. Not really. Okay, let's bring in another one of the lamps that I've got here, and I shall plug it in, and I shall point it at that mat, and we'll see what sort of voltage we're getting, what sort of difference the charge makes. So I'm going to plug it in now, and you can instantly see the meter has gone up to about 0.4, and as I bring it closer, it's gone up above a volt. I would say let's hold it about 4 inches away. This is a good reference. So holding it about 4 inches, 100 millimeter away, it's the best part of a volt. Okay, what about current? If I set this to microamps, and this is where you find how little is involved in the charge. Holding it about the same distance, it's about 0.9 microamps. It's less than a microamp. And as I bring it closer, it will increase a little bit. So yeah, about a microamp. That's all the current that comes out, but that's all that's needed to create a significant charge in the air. Okay, let's put that back round there. Let's unplug that. Let's bring in the Mountain Breeze ionizer, because that's what the other circuit was. The other circuit was that I've looked at this in a previous video. When I got this, that was faulty. There was a bad solder joint in it. Naughty Mountain Breeze. Mountain Breeze ion probe. Made in Britain by SIDAC Technology Limited, SIDAC, Peel Road, Skelmersdale, Lancs. That's interesting. They rate it at 0.3 watts. Ultimately, that would be mostly the Neen indicator. But that's interesting that the PIFCO, the Mountain Breeze, must have been bought maybe by PIFCO, but it was original, made by SIDAC. I'm not even sure how to pronounce that. Here is what was inside the tube. There was a capacitive multiplier with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 capacitors. And it also had a wire going up to the other end for the little Neen indicator, which is removed. Now, here is the thing I mentioned about improving the output. In fact, I'll prove that. Watch this. I'll take this off. This is a little carbon fibre brush I added on. I'll show you how to make them. But initially, I'm going to do a test that I'm going to dangle the needle on the end of this, because this one just has a little needle in a socket, so you can change it. Put needle on the record. Let's just turn this on and hover it round about the same height above the mat. And it's okay, it's not great. The other one was showing about a volt for that, but I have to get a lot closer to get a volt out this. Okay. Now I'm going to put that little carbon fibre emitter on the end, because this is charged up to spicy voltages. So I'm going to shove this onto the end of the needle, and we'll try that again. I shall plug this in, and now when I bring it up, round about the same height, I'm getting that 1 volt again. What a difference that carbon fibre emitter makes. That is huge. And if I turn it round to the current setting, what am I getting if I hold it roughly there? Getting slightly more off this one, but very, very close. I mean, it's only literally tenths of a microamp, but we're talking pretty much 1 microamp again. Interesting stuff. Let me show you that little how to make a replacement emitter for your needle. If you have an existing vintage ionizer and you don't want to have to change the needles in it, this is a very, very easy fix. I should have grabbed another ionizer for this and shown you the fix, but anyway, I shall just go and grab something. Just give me a second here. Regulars to the channel may recognise this. This is carbon fibre heating cord. If I take a bit of this and I strip it like this, just about 12mm, half an inch, and then I cut about the same distance off. I should zoom down in this so you can actually see what I'm doing. So I've stripped this carbon fibre heating wire, which you can buy on eBay, and I'm going to cut it about there. And there's a little thread wrapped around this, which is just to tie all the strands together. It's probably mainly used during manufacturing. And if I cut that little thread off, you don't need to cut that thread off, you could just unravel it. Then what you can do exactly what I did with this one. The existing needle, you can take the other end of that, the core, and you can just stab it onto the end of the needle. And when you do that, that will increase the output of your ionizer greatly, because instead of having one bluntish metal needle, it's now got hundreds of thousands potentially of these tiny little strands. And it's interesting to note when you actually do this, when it's been running for a while, the electrostatic repulsion, they'll actually fan out like a little fibre optic display, and little clusters of dust will appear on the end of them as well. But it's a very easy way to boost your ionizer. And that is about it. I'm just going to get this stuff out of the way because that is potentially still charged and zappy. So that's amazing that they can fit all that circuitry in there. As I say, I still prefer the voltage multiplier one, but this makes it more universal for other countries. Oh, there is something else that's really important to mention. You can get 12-volt versions of these. I want to show you something that's important. Bring the notepad back in again. Notepad. Next page, next page. If you use, and let's zoom down, if you use a little plug-in, so there's the wall socket, let's just draw a couple of pins, and you plug in a 12-volt adapter, and you run it to one of these little modules that then has this sort of end coming out, and it's got the little ion emitter tip. Then, because this is generating a voltage in the region of, could be 5 to 7 kV, but a very low current, it will create a charge in the air, but it will be looking for a return path, and you'll end up with the voltage difference between mains ground and the circuitry in this of several thousand volts. And these power supplies don't have a means for that current to return. So effectively, your circuitry inside, which is got the primary winding, the secondary winding, usually with just a thin layer of tape between them, it has thousands of volts across that, and it will potentially spark across. And this is why I really don't recommend using the little USB ionizers in the either the plug-in USB charger adapters, or definitely not in your computer, because ultimately it's raising a potential difference across the power supply that could make it fail. And if it breaks the insulation down, it could potentially then pass mains. So if you do use the 12-volt one, I recommend that the negative connection on that, if you get a couple of wires coming out, the negative one, I recommend that if you, depending on the power supply you use, whatever you do, just the negative side of that, connect it to a ground reference, preferably in the same sort of, if you put it in a box with a little power supply, run an earth wire into that box, or at the very least, connect it to one of the legs of the mains via a couple of resistors or something, just so it's got a current path that it can get back. That other thing I mentioned about the cable coming out of the unit here and going to the emitters, if you were to break that cable and then you were to just solder in a couple of 1 megohm resistors, that is just a useful safety feature if you're using the mains versions of this, and just sleeve that over in your case, just so that if someone does touch the output, they've got much more in line with them than that horrible little tiny resistor. But there we go. Interesting stuff. You may have noticed that I quite like ionizers. I like the mystique that applies to them. So, inspired by another channel, I'm going to provide a couple of links to other channels for your lockdown recreation. This is being filmed during the viral lockdown that's going around the world at the moment. So I'll provide some links to other channels just in the vicinity of here. And for entertainment, I'm going to provide a link up to Fran Lab, because Fran put up a video recently about a digital display that is like really old electromechanical technology, but kind of electronic-y, but electromechanically. It's fascinating, so it's well worth looking at that. So that's it. I shall finish the video now and go and play with my high voltage modules.